So in this video, we're going to learn about the two views for sequence numbers and acknowledgement numbers in TCP segments that Tcpdump has available. So let's start off with the pcat file. I got one that's called google.pcat, which just contains a request to Google. And I'll go ahead and print out the first 3 packets. So by default, Tcpdump will use relative acknowledgement numbers, though only after the three-way handshake, and up, not just, I guess, the completion of the three-way handshake, but up until the last segment of the three-way handshake, this one. This is where it starts to use the relative sequence numbers. For the SYN bit that's sent out in the TCP segment that says, hey, this host of 10.0.2.15 wants to synchronize with google.com on port 80. The google.com on port 80 responds to my host and says, yes, I'll synchronize with you. And it does this by confirming that. And then it's a way to say, or I should say, acknowledging that. And then in this packet, an acknowledgement number appears right here. In addition to acknowledging my request for synchronization, the Google server then asks to synchronize its connection with me. And then I respond, I of 10.0.2.15, respond to Google in the last part of the three-way handshake and say, I acknowledge your request to synchronize with me. So we're both synchronized to each other now, which is 2 flows in each direction, making a connection. And let's take a look at, actually just to break from this for a moment, let's move to the TCP header. So I just Googled for TCP header and images and found one. Let's see if I can actually bring this up. Yeah, okay. So here we have the sequence number. It comes after the destination port, and the acknowledgement number. These are both 4-byte fields. Another way to say this is they're both 32-bit fields, so they can fit a pretty large number in there that has a value of over 1 billion. Now, you may ask, what are these numbers for? Well, these are both numbers together are used to keep track of bytes between each side. And this is used in TCP for things such as retransmission of lost packets. So going back to our example of relative sequence numbers, we see that there are 2 absolute ones, so that is the full sequence number is printed there, and then we begin the relative ones. So again, Tcpdump only prints the relative numbers after the three-way handshake is initiated, and does it for the first 2 packets, but not the third. And then after the third and after for that connection is printed in relative sequence numbers. Otherwise, it's absolute. So let's just go ahead and print the same thing using absolute sequence numbers. So to do that, we can use the -S option. And now you can see sequence number here, and the acknowledgement numbers in there are all the full 32-bit number. So now let's do this again and clear the screen here and print the first 5 packets. And you can see that here again, they are all absolute, but now we're gonna do it in a way that prints them in the default mode of relative. Okay, so now you can see only the first 2 and the rest are relative. ACK1 through 109, and our sequence numbers 1 through 109, and ACK109. Let's explain this a little bit. So in the TCP segment, when we're synchronizing with the host, we're setting our first sequence number. This is chosen by the operating system, specifically the network stack code. And it's called the ISN, or the initial sequence numbers. There's different algorithms for this, but this is just chosen. Then, that is what it's actually used to sync with the other host that this connection is working with. And then in our case is Google server. So whenever I receive, or when the Google server receives, this is Google right here, the request, he sets his sequence number, okay? And he also sets his acknowledgement number. But the reason why he has an acknowledgement number in this case is, again, as told before, referring to this is a way to acknowledge the sender's SYN. And he does that by saying, hey, I'm going to increment this by 1. So the formula here is ISN, or initial sequence number, plus 1 for the beginning of the three-way handshake. So you can see that the last 2 digits is 77, so he increments it by 1, and he acknowledges to 78. That's a 1 byte acknowledgement from the packet. Next, what actually happens is the client, that is me, originating the request to google.com, then sets my ACK acknowledgement number 1 more than his sequence number. But here we turn to relative sequence numbers, and so it's not clear what that looks like. So we can actually just quickly move back to the absolute mode here again. And you can see, here it is, there's the sequence number, and then my acknowledgement number in this case is, again, 1 more, the ISN plus 1, than the sequence number of the packet prior. So let's go ahead and clear the screen and go back to the 5 count that are relative sequence numbers. And now you can see that me, that is the client, sent the GET request to google.com and asking for their website page, their web page. And the sequence number I have is, in the relative form, is 1 through 109. And if you think about that, that is actually 108 because we're starting at 1. And you can see that the length of that packet contains 108 bytes. Then the Google server responds, okay, and acknowledges the 108 bytes by saying ACK 109. So here again, we're pressing 1. We're saying, hey, 1 more byte, because that was the difference, because there's no data being carried in this particular segment. We're just saying, because you can see length is 0, we're just acknowledging that, hey, we got yours, and that increments it by 1 if there's no actual data being sent. Okay, well, I hope that kind of clears some of the stuff up on TCP sequence numbers in Tcpdump. Okay, thank you. Tcpdump allows you to set the buffer size of libpcap in cases where there's more packets than your system can keep up with, and the buffer that happens to be there overflows, and the result is that Tcpdump has to discard packets. They're not able to get processed. They are thrown away at the kernel. So this option of Tcpdump that allows you to specify the buffer size is -b. You can also use -buffer-size. But we're going to use -b for short. And it is measured in kilobytes, so 1024 bytes. And to pick a number, so by default, it is set to, here I'm looking at the pcap.linux.c code for libpcap. And the default buffer size is 2 megabytes, right here, for the ring buffer. So if you need something more because you have a high rate of traffic coming, you can specify it on here. So if we want to increase it to 4 megabytes, what we can do is we can see what the number would be. So 4096 divided by 1024, because I'm going to specify 4096, and that is 4. So 4 megabytes. So what we're going to do is we're going to say, hey, Tcpdump, I want to set a buffer of 4096 on this interface, and what I'm going to do is let it print to the screen. I'll give it sudo. There's really not much going on this interface. Let's try the other one. Yep, coming in, and you can see that 15 packets were dropped by the kernel in this case. Let's try it again. Quick kill it. 40 packets were dropped by the kernel. So what happens if we increase this number? So let's do echo 4096 times 2. We have 8,192. 8,192, and see what happens. 2, 3, 4, 5. You can see that 0 packets were dropped by the kernel. Let's try it again. 1, 2, 3, 4, 5. Only 1 packet dropped by the kernel. But you can tell that we're already doing much better than we were whenever we set the size to 4 megabytes. And then we can actually increase it. So again, let's do it multiplied by 3. 12,288. 12,288. Okay. Oh, sorry. 1, 2, 3, 4, 5. 0 packets dropped by kernel. 1, 2, 3, 4, 5. 0 packets dropped by kernel. Excellent. So in this case, we increased it large enough that we were not able to drop any packets for the time that we were capturing. Great. So that concludes this video.